Hello and welcome to another video in machine dynamics. And with this video I would like to start a series of videos on modifications of the classical Jeffcott rotor model, which you have seen in the last video. So now what I'm dealing with are additional effects. What kind of additional effects are there? Well, for example, there could be a pre-deformation of the shaft. So the shaft is not in ideal position, initially not in ideal position, and we have to deal with relative displacements instead of absolute displacements when we consider the elastic forces. Next, the bearings are initially assumed as being rigid, but of course you know that there could be some deformation also related to the bearings, namely there could be some kind of elastic effect, some kind of flexibility in the bearings, and this effect will also be taken into account here. Next, we assume that the shaft is circular, perfectly circular, and as you know, real shafts are not perfectly circular but are non-circular. This leads to a big modification, I would say, of our classical Jeffcott model, and this will be discussed here when we deal with non-circular shafts. Finally, there could be the influence of gravity that we take into account. At the moment did not take into account, but will take into account here. Then there could be some inner damping in addition to the external damping we already considered. And of course, what also could happen, that there is an inclination of the disc, so the disc is not mounted perfectly perpendicular to the axis of rotation, and this effect will be also taken into account here. Now, as you can see, this is a long list of effects, and one video would simply be too long to discuss all these effects. So therefore, I would like to start in this video with the first two effects and then produce a series of videos on the other effects as well. What is the objective of all these modifications, of all these additional investigations here? Well, as you learned from the previous video, you saw that we are focusing on the stationary state, because then the equations of motion decouple. So in this study, we are also dealing with the stationary state. And then the question is, what is the influence of these additional effects on the stationary solution, on the stationary behavior of the Jeffcott rotor? So let's discuss what was the important effect, or what were the important effects in stationary state of the classical Jeffcott rotor. Well, there were two. They were summarized as theorems of de Laval. The first was that there is resonance or danger of resonance if the rotational velocity of the rotor comes close to the so-called critical speed, so to the resonance or natural frequency of the rotor system. And the second is that we looked at the asymptotics, and especially for quickly rotating rotors, so for fast rotors, we have the self-centering effect. So when we discuss these additional effects, the focus is first of all on these critical speed. I would like to say even critical speeds, because we will see that there are several, or there could be several critical speeds if we discuss these effects. So the first question is, what happens to the critical speed or to critical speeds? Is there just one? Is it affected by these additional effects? And if yes, in which sense? Will the critical speed increase or decrease? And will there just be one critical speed, or will there be several critical speed? And spoiler, I could give you the answer here. There isn't only one critical speed. There are cases where you have several critical speeds, and even where you have a whole interval of critical speeds that you have to avoid. That's what you will learn, basically what you will learn from studying these effects. Then, of course, it's a nice exercise in different formulations of dynamical problems, and it's a nice exercise also in understanding a little bit better these equations of motions. They look quite simple. They are linear, second order, ordinary differential equations. But you can see, or you will see, and you will learn that they can have various effects here. They can have critical speeds related to the homogeneous solution and critical speeds related to the particular solutions of these linear ordinary differential equations. So what appear to be quite simple in, for example, engineering mechanics 4, when you studied the single degree of freedom oscillations, and where these linear ordinary differential equations of second order looked really, really simple. What you will discover here is that there's much more complexity in the solution that might affect the dynamic behavior of rotors of machines. Okay, let's start with the first effect here with predeformation. So what is predeformation? Predeformation means we have plastic predeformation in that sense that, as you can see in this figure, the rotor assumes an initial state that is already deformed, and from these initially deformed, plastically deformed state, the elastic deformation of the shaft starts. So when we look at the position of the center of the disc, then we can see that it is described first by the plastic predeformation, which means that the center moves from this theoretical position, which is still the connection line between the centers of the two bearings, to a point W0. And from this plastic predeformation, when elastic deformation starts during rotation, then that point moves, or the center of the disc moves to point W, which is the connection point. So the connection point between shaft and disc moves to point W, which is now the actual connection point between shaft and disc. So basically, as the center of gravity is not influenced by this, or it's just at the same relative position with respect to point W, nothing changes much for the inertial forces. However, as we have to apply the restoring forces to point W, and as the elastic restoring forces, so I'm not talking about the damping here, but about the elastic restoring forces, depend on the displacement of point W from some initial condition. We do not have the absolute displacements. We do not have to take the absolute displacements between W and the ideal point O into account when we are talking about the elastic restoring forces, but we have to take the relative displacements between W and the plastic predeformation W0 into account, because everything where point O moves to point O, everything that is related to the displacement between point O and point W here, so the initial displacement is due already to plastic deformation or predeformation and not due to the elastic restoring force or to elastic deformation, and therefore does not lead to any elastic restoring force. So let's summarize this argument. So the elastic restoring force of the shaft is now given by the relative displacement between the actual point W and that plastically predeformed initial point W0. The initial point W0 is described here by some initial radial displacement E0, and then there are cosine omega t and sine omega t to distribute that part on the y and the z axis here. So these are the relative displacements we have to take into account when we are talking about the elastic restoring forces. All the other equations for the Jeffcott rotor, for the classical Jeffcott rotor, remain unchanged. So therefore, our equations of motion, of course, for stationary operations, so we just concentrate now on the vertical and lateral displacement of point W here. They remain unchanged for the inertia part. Keep in mind that the inertia part has two parts. The first one sits on the left-hand side, and the second one, which is the rotating imbalance here, sits on the right-hand side. The damping part remains unchanged. And now for the elastic restoring force, if you insert relative displacements instead of the absolute displacements, you will find omega k squared y w on the left-hand side, and we put the time-dependent part, which is omega k squared E naught cosine omega t for the first equation. You can see it, we put it on the right-hand side because it acts as an excitation here. Same holds for the second equation. And as you know, the third equation is not considered here because we are assuming stationary operation. And what you can also observe is that the two equations are still decoupled. They are also still linear ordinary differential equations here. So just the right-hand side changed. So there's an additional term on the right-hand side, and you know that you can still apply, of course, the superposition principle. So you can superpose the solutions, and especially if you consider the particular solutions, and let me repeat why you should consider particular solutions here, only because you have damping, and due to the damping, the homogeneous solution will decay exponentially if everything works well, because you have only light damping here, because you want to have a very energy efficient rotor system. So therefore, we are considering particular solutions. And due to the superposition principle, we can consider the particular solution for each term independently and add them up at the very end. The first part is known to you. It's the particular solution with respect to this term. Let me remind that there's a small modification here. You can see that phase shift phi naught here, which is introduced because for the plastic pre-deformation, we assume that it is aligned with the two axes here. You can see there is no phase shift here in the relative displacements. So in the displacements, in the second part of the relative displacements, which belong to point W naught. And therefore, we have to take them into account because we cannot assume that W naught and W are perfectly in a radial position. Why should that be the case? Yeah? So therefore, this tiny phase shift phi naught appears here, but it will not have any significant influence, of course, on the discussion of the solution. So what can be said about the second part? Well, I would say also for the second part, of course, you are quite familiar with that kind of external excitation, because it's just a harmonic function that we take into account. You can see that the amplitude is a constant. It's completely determined by the parameters of your system, E naught and omega k, which is the critical speed, but also the resonance or natural frequency of the system. You see that that additional particular solution is just given by E naught and V, which is the classical magnification factor, the magnification factor for a harmonic solution due to an external force. So we are dealing here with the case of an external force, not with the case of a rotational or rotating imbalance. That would be the case for the first term of the right-hand side of the excitation. What you observe is that still all the coefficients in these two equations are identical, except for the harmonic function, which is now changed. In the first equation we have a cosine, in the second equation we had a sine function. And therefore, the particular solution is assumed as a cosine and with the sine function here. And then it leads to the same phase shift for both terms, and to the same magnification factor. And this phenomenon leads to the fact that we still have a circular motion around zero if we just consider this particular solution. If we now consider the total particular solution, then it's a composition of two circular motions, namely one circular motion with a certain phase shift, phi naught minus epsilon here, which is related to the imbalance. So it has a different amplitude, e eta squared v, the classical eta squared here for the magnification factor or that we consider if we have an imbalance is taken into account here. A v refers now to that magnification factor without that eta squared, so therefore the eta squared appears here as a factor in front of the cosine term. And the term we discussed here, E naught omega k squared cosine omega t minus epsilon v. So we have two circular motions that are superposed. What can we say now about the asymptotic solution here? The asymptotic in the sense of what happens if we have a low rotational speed or if we have a very high rotational speed. So if we are close to the static case or if we are if you are considering a very high speed rotor here. That will be shown on the next figure. So here you have the superposition. First, we consider the case of imbalance, and then we consider the case of pre-deformation, and then we superpose these two solutions. So you see again here the magnification factor and its behavior with respect to eta. Here you can see for the imbalance the magnification factor, the classical magnification factor for an external excitation by a force, or by a spring, for example. And here you can see it has to be multiplied again with eta squared. And of course that factor eta squared here changes a lot the asymptotic behavior of the solution. While for an imbalance you start at 0, static case, so no displacements, and you end up with, if you normalize the results, of course, with 1. For the other case, the pre-deformation case, you would already start with an initial deformation with 1, and you end up with 0 here. So if now you add up the two cases, what you will see is the following for the asymptotics. If omega is 0 or tends to 0, so the rotational speed is very low, then for the imbalance there's no displacement. From the pre-deformation, so the additional effect we considered here, you already have the pre-deformation, so you already have your E naught here, your initial displacement, because you start in the pre-deformed state, because you start at W0 and not at 0. Yeah? So this would be a possibility to determine the amount of pre-deformation in your system. Yeah? If you have a rotordynamic system and you want to know how much pre-deformation is there in that system due to mounting the rotor or whatsoever, then use a very, very low rotational speed, possibly 0, could also have a very low rotational speed, and then start to measure. So if you have to measure during rotation, then just decrease the rotational speed as much as possible to determine the pre-deformation. On the other hand, when it comes to omega tends to infinity, then the effect of the pre-deformation will vanish, but what remains is the effect of the imbalance. And this effect of the imbalance has been studied in the video before on the classical Jeffcott rotor. And as you know, theorem of de Laval, there is a self-centering behavior. And as this is the dominant part of the solution from these two solutions that we superpose, this will be also the dominant part here for our case. So we still have a self-centering behavior when it comes to plastic pre-deformation. So basically, there is not, I would say, not much change if we take plastic pre-deformation into account. Just let me remind to you that you can determine the amount of plastic pre-deformation for low-speed rotors, and it will be present in low-speed rotors for high-speed rotors due to the self-centering behavior. You can neglect this effect. Now let's move to Another example, to the second, of additional effects I mentioned on the first slide of that video, namely the elasticity of the bearings. So forget again about everything that has been taught on plastic pre-deformation. We study a new case here, so we study each case separately from the cases before and try to learn something from each case independently. And what I consider here, as you can see, are these springs that represent now the elasticity of the bearings. Let me mention how these springs are introduced here. They have different spring constants, so C sub H and C sub V. H stands for horizontal or lateral direction, V stands for vertical directions, and these two directions are the space-fixed directions. So what I do not consider here is some, I would say, a rotating elasticity in the sense that these spring constants rotate with the system. We will do this later on when we consider non-circular shafts. So in another video I will consider these effects, but not here. So here for the moment these spring constants are real constants in a space-fixed coordinate system, but they can differ in lateral and vertical direction. Now what will happen due to these springs? Well, due to these springs we have another shift, and this time what shifts is already this center, this ideal line, which includes the center of the two bearings. So O would, for example, correspond to the situation where these springs are not stressed, so where the spring force is 0, and then you increase the displacement, you will get a first restoring force due to these springs, and point O then moves to point O prime. And then you, of course, also have the elastic deformation of the shaft. The shaft is still now at point W, but now you have the displacement between point W and point O prime, which yields the elastic restoring force of the shaft, while you have an additional restoring force for the displacement between point O and point O prime, and this is the restoring force that is due to the left and the right bearing here. So this is the situation. If I write down, well, you can see the diagram here, and again we mark for each point O prime, W and S, we introduce coordinates. For the point O prime, they are denoted by Y sub L and Z sub L, which comes from the German word Lager instead of bearing here. And now if you consider the forces, then we have the restoring force of the shaft, and for the restoring force of the shaft we still have one spring constant C for the elastic restoring force, and we take into account the relative displacement now between point W and point O prime. So therefore we have Y sub W minus Y sub L. Y sub L is the lateral displacement of point O prime. And then we have the restoring force of the bearing, which is now Fy, and then with a superscript L, C sub H, Y, L, and in Z direction, in vertical direction, we would have C sub Z, Z, L here, C sub V, sorry, Z, L here. Now, the derivation of the equation of motion becomes a little bit more involved, because on the one hand, we have to take into account the free body diagram of the disc and the shaft, which is the same as before, of course, but then we also have to consider a balance of forces at the end of the of that shaft, so at the both ends of that shaft, the left and the right end, a balance of the elastic restoring forces that relate to the bearing on the one hand, and to the shaft on the other hand. This is shown on the next slide. So here you can see the two free body diagrams we have now. The left one refers to the situation at the bearings, so this would be the shaft here, and on each end of the bearing, it's just shown here for the lateral direction, we would have the lateral restoring force, and well, in the middle where we would have the disc, we have another restoring force here, which is the restoring force related to the elastic shaft. That restoring force of the elastic shaft will be found, of course, if you consider the balance of forces for the disc, and then you have to add, of course, here the inertial forces in the sense of D'Alemberts or negative, pointing in negative direction, and they sit at the center of gravity still, and the restoring force acts at point W. So this is not seen here. You have to enlarge that point in order to see this effect, but it's of course well known. The right diagram, I guess, is well known for you from the last video and from the discussion of the classical Jeffcott rotor. So let's introduce the force balance here for the shaft. So for the shaft, you can immediately see that you have 2 times F YL. And on the opposite side, you will have, so the balance is with respect to the elastic restoring force of the shaft. So if we introduce the spring coefficients and the appropriate displacements on the left and on the right hand side of that equation, then you get a first equation, and this equation allows you, for example, to determine y sub L, because for the right system, you still know that this is an ordinary differential equation due to the effect of inertia, of course. An ordinary differential equation that allows you to study the displacement y sub W. So we need another equation, namely this one here, to determine first the displacement y sub L. Yeah? So for the disk, we have our ordinary differential equation where we now have to plug in the elastic force. Let me note here that we do not consider the damping because we are interested here in the critical speeds and not so much in the effect of damping. We know that the damping is there, small damping is there, but we do not consider it explicitly here. If you want to do this, then you have to add an additional term here. Then you insert Fyw. You can see it's the same term as before, as here on the right hand side. And for the inertia force, you split it again in a term appearing on the left hand side related to point y sub W, and the term related on to the right hand side to the excitation here. And let me remind that we are considering and focusing only on the stationary state. Only then this decomposition is possible. If not, you would have an additional term here and the equations would be coupled. No? You see that it's really necessary to determine y sub L beforehand, and it's good that we have this balance of forces here that allows us to compute y sub L. So we plug in this result, and then we are interested how the critical speed is modified, because you can easily see it's not C sub m anymore, which is the resonance or natural frequency of the system. We do not consider any damping, but that this is modified if you insert the term for y sub L, because y sub L depends also linearly on y sub W. Okay, so if you plug in y sub L, so this solution from the first equation into the term, and then add C, so you will have a C squared for the second term, and for the first term you have to take C plus 2CH into account on in the numerator and in the denominator, and then you will end up with just the term 2 times C sub H divided by 2CH plus C and the C here. The same can be done for the second equation, of course, with a slight difference. Now, I could say two slight differences. The first one is known to you on the right-hand side. There appears the sine term and not the cosine term, from the fact that we have to replace z sub s with respect to the center of gravity by z sub w using the classical kinematic relationship explained in the last video on the Jeffcott rotor. But the main difference is now here. C sub v instead of C sub h. So due to the fact that we consider different stiffnesses in lateral and vertical directions, these coefficients are now different, leading now to two different critical speeds. So this is the first case where you discovered that there can be several critical speeds, and I would say it completely makes sense that you have different critical speeds here because of the fact that the stiffness coefficients are different, that we do not have isotropic conditions in that bearing. Yeah? So let me summarize these critical rotational velocities here. We compute them by dividing the equation by m, and then either we take omega k squared here or we have to take the root of that expression. So what you get as a first term here, c divided by m, as the first factor, is omega k squared related to the classical Jeffcott rotor. And then there is an additional term, and now let's discuss this additional term. You can see it's 2c sub h divided by 2c sub h plus c. If you look at the term, then you can see that the denominator is always larger than 1 and therefore larger than the numerator, so the whole expression is always smaller than 1. This means that omega k squared is always larger than omega k1 squared because you have to multiply omega k squared by a factor that is smaller than 1 to obtain omega k1 squared. Yeah? So this means that the critical speed for for elastic bearings, so taking the stiffness and the flexibility in the bearings into account, is smaller than the critical speed for the classical Jeffcott rotor. So if your task is just that you want to be in the supercritical range, you can take, even if you have flexibility in the bearings, you can take the solution with respect to critical speeds, of course, the solution from the classical Jeffcott rotor, and you know if you are in the supercritical range for the classical Jeffcott rotor, you are also in the supercritical range if you take elastic deformation of the bearings into account. If you would take this effect into account. So if this is simply your task to be in the supercritical range, I would say the solution from the classical Jeffcott rotor would be sufficient because any flexibility in the bearings would lower the critical speed. So you do the same for the z direction. You see the computations are the same and the conclusions are the same from that result. And let me summarize this result. We do have two critical rotational velocities. If c sub h is not equal to c sub v, if they are equal, of course, then the two terms will match and we just have one critical rotational velocity here. And finally, there is a reduction of the critical speed of that rotor due to the flexibility of the bearings. Well, this is the end of this video. You have seen two effects, I would say two rather simple effects. We will discover more complicated effects in the next videos. You have seen that if you have pre-deformation, then this matters for cases where you have low speed rotors, where you are close to the static case, and that's an ideal opportunity to measure or to determine the plastic pre-deformation, while for the asymptotic result, nothing changes. If you consider the flexibility of the bearing, then you can see that that flexibility affects the critical speed. It reduces the critical speed. And if you have non-isotropic situations, so non-isotropic stiffness in the bearing, then you will have multiple, namely two critical rotational velocities. This is the end of that video. I hope you like it, and you will see and discover the next effects in the next videos, and these effects, as I said, will be a little bit more complicated. Thank you very much for your attention.